In this example, we are asked to try to find a power series representation of this rational function. So what we're going to do is, and then all we're asked about is the radius of convergence of this one. But what we're going to do is break this function into two parts. One, which is a polynomial, just x squared, times the other portion, which is this rational function, okay? And what I would like to do is notice that this term right here, this 1 over 1 plus x cubed, is not necessarily geometric. It's not geometric, right? So let's just look at this portion. 1 over 1 plus x quantity cubed. And let's think about how could we make this look geometric, right? So our goal in this entire section has been to try to get to a point where we can write at least a portion of a sum that looks like, so a naught r to the n, because we know that the sum of a convergent geometric series looks like this, right? So this is where r is less than 1. So we want to try to get our rational function to look like this. Constant over 1 minus something involving x. All right, well, this is not the way it looks, right? Because right now we have a quantity cubed on the bottom. It's not just x cubed. If it was x cubed, we could deal with it, if it was just the x. But it's not. It's the entire quantity cubed. And so in our minds, we want to think about how can we reduce this power? How can we reduce this power, right? And you might remember that this can be done by integration, right? This function can be written like this, 1 plus x quantity to the negative 3 power. And then we can integrate away these powers, okay? So the integral of 1 plus x to the minus 3 dx, this one is going to equal what? The new power is going to be negative 2, so negative 1/2 times 1 plus x to the negative 2. And then we have to do this one more time, right? So then we integrate this again. And we end up with, the new power is going to just be a negative sign, so positive 1/2, 1 plus x to the minus 1. All right, so we've taken two integrals, and we've gotten this function. So now we have 1/2 over 1 plus x, but this can be represented in terms of our geometric sum pretty easily, because this is 1/2 over 1 minus negative x, right? And so without any work here, we can just write down, well, we've done two integrals, right? But other than that, we can just write down the fact that this function is the sum of this geometric series, right? So it's the sum of a geometric series, so this can be written as n from 0 to infinity of 1/2 times negative x to the n. And of course, this whole thing can be then written as an alternating series, negative 1 to the n times 1/2 times x to the n. Okay? So this is now by the way, we've integrated twice. We now need to take two derivatives to get back to our original function, remember that our original function is just this portion, right? It's just this portion of our function. So let's do it. So right here, let's call this function like, let's call this q for, I don't know why q, but let's call this q of x. And this is the sum, n goes from 0 to infinity, negative 1 to n. I'm just copying it down. X to the n. And I want to take two derivatives of this, because I need to undo the two integrals that I did to get this formula. And so q prime of x, this is going to be the sum. N goes from 1 to infinity. Remember, when you take a derivative, you cancel out the constant term, right? And so this is gone, and you end up with then negative 1 to the n times 1/2 times n to the x times x to the n minus 1. And then you do it again. So q double prime of x is the sum. N goes from 1 to infinity, negative 1 to the n, 1/2 n minus 1, x to the n minus 2. Okay, and this must be the power series for this function. So this is 1 over 1 plus x quantity cubed. Why? Because we have derived out, taken the derivatives of the integrals. So we've undone the integrals that we did to get this power series in the first place. By the way, it's a little subtle what I've done here, and I've totally left it off, right? But technically, when you integrate, you get a constant here, so c1, and then here you get a plus c1x plus c2 on this term, right? This stuff I've left off of my power series entirely. It's added on to this, but look what happens when you take the two derivatives. That's going to get be gone anyway, right? So because I knew I was going to be reversing the whole process, I didn't add in, or I didn't include my constants of integration, but I should have. Okay, I should have. You shouldn't ignore them completely, because you can't be sure that they're not going to contribute unless you've thought about it. Okay, so you should at least think about it. But after taking the two derivatives, this is gone. Okay, so it's gone, and we're back to just this being our series. Now, I made one mistake here which you probably caught and screamed at me for, but that should have started at 2. Every time you take a derivative, it bounces up the index by 1. And so the last thing I'd like to do here is, well, I'm going to leave it like this because this is not our function, right? So q double prime is not our function. Our function f is that q double prime times x squared, right? So now we have to go back here and write our function f of x, which was x squared over this entire denominator. This is x squared times our power series, right? So this is x squared times the sum. N goes from 2 to infinity, negative 1 to the n, 1 half times n minus 1 times x to the n minus 2. And at this point, we can take this x squared and multiply it in, combine it with these ones, right? Okay? And so we end up with then our function f of x equal to the sum n equals 2 to infinity. It starts at n equals 2. Negative 1 to the n times a half times n minus 1 all times x to the n. So there's a power series representation of our function x squared over 1 plus x quantity cubed. Now, the question of the radius of convergence was actually answered way back here, kind of. So we could have addressed it at this point, right? Because this is where we chose our radius r. And remember, this only converges when r is less than 1. R is equal to negative x, and so x is less than 1. And then that means that the interval of convergence of the original series that we were working with was x between negative 1 and 1. What did we do with that series? Well, after we found that series, we took derivatives of that series. And so derivatives will never add information. Okay, they never add information to your interval. And so this is the interval of convergence of this series. So you might remember in the last example, we had to check the endpoints of our interval because we got the new series by integrating. Okay, by integrating. This time we got the new series by differentiating, and differentiating can never add information. So our open interval is exactly the correct interval where these two functions agree.